Hi, my name is Mac Ernest, and today I will be doing a video solution for impulse momentum bouncy ball problem from Lon Kappa. So, the problem says a super bouncy ball with a mass of 0.5 kilograms falls from rest starting at a height of 31.2 meters, which I drew as event 1. So that dot is the ball. It is falling a distance of 31.2 meters. And the ball rebounds upward to a height of 20.7 meters after interacting with the ground. So I drew that as event 2 with the dot representing the ball again and it going back up a distance of 20.7 meters. It says to ignore air resistance, so we don't have to take that into account. What is the value of the impulse the ground experiences due to interaction with the super bouncy ball? Consider up to be positive and down to be negative. So, for part A, first we solve for VF, or velocity of the ball before it hits the ground. So we use the kinematic equation VF squared equals VI squared plus 2AD, which would become VF squared equals 0 squared, at least initial velocity is 0 because the ball is being dropped from rest. Then you're adding 2 times gravity, negative 9.81 meters per second squared, times negative 31.2 meters because that distance is downward. You take the square root of both sides, and you get VF equals plus or minus 24.7415 meters per second. The direction of the ball is downward, so V must be negative. So we choose the negative 24.7415 meters per second as our velocity final, or the velocity of the ball just before it hits the ground. Now we need to find the velocity initial, or the velocity just after the ball bounces. So we'll use the same kinematic equation, and this time velocity final is 0 because when the ball reaches the apex of its motion, it will have a velocity of 0. So we plug in our acceleration value. Acceleration due to gravity is negative 9.81 meters per second squared, times our distance upwards this time, which is 20.7. Notice how it's positive. Then you add 406.134 to both sides. Take the square root of both sides, and you get plus or minus 20.1528 equals velocity initial, or the velocity of the ball after it bounces. Velocity has to be greater than 0 because the ball is moving upwards, which we established is a positive direction. So VI will be that positive 20.1528 meters per second. Now to find the impulse, we need to do the mass times the velocity of the system. In this case, we have the velocity of the ball before it hits the ground, just before, and the velocity just after it hits the ground. So 0.5 times our plugged in velocity values gives us an impulse of negative 22.45 kilogram meters per second. So just to be clear, we were measuring the impulse the ground experiences. So the ground would experience a negative impulse because the ball is going upwards after the contact. So this force would have to go in the opposite direction. So it would be negative 22.45 kilogram meters per second. Now, question B asks if the interaction between the ball and the ground only lasts 9.34 milliseconds, what is the magnitude of the average force exerted by the ball on the ground? So, using conservation of momentum here, the absolute value of the change in momentum equals the average force times the change in time. Now we're given a time, 9.34 milliseconds. We're trying to find the average force, and we're given a change in momentum, which was negative 22.45, but when you're measuring change, typically you use an absolute value. So 22.45 equals average force times our time, which we converted into seconds instead of milliseconds, and then you divide both sides by that time, and you get the average force exerted by the ball on the ground is 2,403.34 newtons. And then for part C, it's asking, since the collision occurs between the earth and the ball, what is the magnitude of the velocity change experienced by the earth? So for this one, we know that momentum will be conserved in this interaction. So we'll use our momentum that we found earlier. Earth's momentum would be positive here, And then we have our Earth's mass, which is 5.972 times 10 to the 24th kilograms, times our unknown velocity, or the change in velocity of the Earth. So, let's see here. We have, we'll divide both sides by our Earth mass. So our momentum divided by our Earth mass, and our velocity will become 3.75921 times 10 to the negative 24 meters per second. Now, just to be clear, that is the change in velocity of the Earth. If the super bouncy ball were replaced, this is part D now, with an equal mass sticky clay ball, what would be the value of the impulse ground experiences due to its interaction with the clay ball? So this time, we only need to sort of look at the value for velocity that occurs before the collision with the ground. So our V final that we found earlier, the speed of the ball before it hits the ground, we're going to use that. We're going to use our momentum equation or / our impulse equation. So P equals mv, our mass stays the same, 0.5 kilograms, times our velocity of the ball just before it hits the ground. Because the ball sticks to the ground, doesn't come back up, so we don't need to take into account the velocity after the collision. So what we want to do is just multiply that mass times our velocity, and our impulse is negative 12.37 kilogram meters per second. So the impulse that the ground experiences due to its interaction with the clay ball is negative 12.37 kilogram meters per second. And finally, E is asking which object of equal mass experiences a greater magnitude impulse after interacting with the ground, the super bouncy ball or the clay ball? Well, naturally, the super bouncy ball will have the greater impulse magnitude because the velocity of the system will be higher given that it bounces back up. So, as the clay ball sticks, it doesn't have like an upwards velocity, whereas the super bouncy ball bounces up with a pretty high speed. This will affect the velocity of the system, and if the velocity of the system is higher, we can expect the impulse of the super bouncy ball to be higher. That's it. Thanks.